Hello, our project is titled Information Network Continuous Monitoring Framework to Operate, Secure, and Defend. Our team members include Addison Ladiero, Jenny Faust, and myself, Roberto Bellido Diaz. The Department of Defense Information Network is a vast and complex network presenting significant challenges in terms of management and maintaining a comprehensive operational overview. With its various interconnect authorities and the intricacies of the three key mission threats operate, defend, and secure, an integrated, scalable, and adaptable continuous monitoring framework is essential. Thus, a framework would enable commanders to make informed decisions and operators to operate at the speed of cyberspace warfare, ensuring that the force maintains an information advantage. Our project aims to develop scalable models that can differentiate between malicious and benign network traffic. By doing so, we seek to provide Department of Defense information network operators and commanders with timely and accurate information that aligns with the pace of the cyberspace warfare. Addressing this challenge is critical to ensuring that the force maintains its competitive edge in the rapidly evolving domain of cyberspace. We use two datasets, a Kaggle dataset and a dataset from the University of New Brunswick's Canadian Institute of Cybersecurity. The features that we selected from the dataset include the destination port, flow duration, protocol, total forwarded packets, and total packets in the backward direction. The response variable titled label initially include the 6 types of attacks. For our implementation, we trained the following classification models to determine whether the network traffic is malicious or benign. First, naive Bayes. This was chosen because of its ease of use and speed for prediction. 2. Random forest. We also choose the random forest to create the classifier decision trees, which takes the average of all the individual trees to classify the traffic as benign or malicious. And CNN. Finally, we also tried training a CNN model to leverage a deep learning method. The feasibility of using machine learning models and data mining techniques to detect malicious traffic lends itself to the following use case. Our overall goal of trying naive Bayes, random forest, and CNN models is to prove the utility of machine learning and data mining as part of a continuous monitoring framework for network operations. Our results show that using random forest model has a high accuracy in detecting malicious traffic. Consequently, this can guide a commander's decision in resource allocation to restore a network's running status. For example, suppose that there was a network outage and the network intrusion system validated that the outage was not due to a denial of service. If the traffic was malicious, the commander can swiftly prioritize the defend mission threat to alert network defenders of a potential incoming denial of service attack and report the general location of the attack within the network. Evaluation of results. We have naive Bayes. As mentioned before, we initially choose to try a naive Bayes model for speed. The results from naive Bayes shows an accuracy of 0.74 when predicting malicious traffic and an accuracy of 0.84 when distinguishing between benign and malicious traffic. However, the random forest performed better than the naive Bayes with an accuracy of 0.9903 and a distinguishability score of 0.991. And the CNN model, the first CNN model using the select features DST port flow duration, protocol, thought forward packages, and total backward packages showed an overall accuracy of 0.75. The second iteration of the CNN, which used all 79 features, had a higher accuracy of 0.885. To reflect on the three models we've discussed thus far, Random Forest has the best performance. Although the neural network models did not perform as well as expected, we could further tune the models to increase their accuracy while being careful of overfitting. Furthermore, our current implementation has a few limitations. The first is that the data set we used was generated on a test network. Even though Random Forest has performed well on this data, we would need to continually tune the models when using new data from a live network. The second is that the data used is relatively small and thus good for creating proof of concept results. Future work would require a thorough analysis of data volume and compounding needs at much larger scale and an assessment of the appropriate technologies and platforms to best suit this line of work. Interconnectedness of these authorities and the complexity of each mission threat operate defend secure demands a continuous monitoring framework that is integrated, scalable, and adaptable. This research shows that machine learning models can detect anomalous traffic with high accuracy and, when coupled with artificial intelligence, will better enable commanders to understand, visualize, and describe the information network environment and shorten the time it takes to direct action. These solutions will ultimately help pull the complexity up to reduce the demand for technicians, which also aids in the Army's war for talent and resources.
Up to this point, the exploratory data analysis has been completed. The data has been discretized and label encoded. The dependent variable label is evenly distributed to prevent bias. We'll use a 80-20 test train split and run the algorithm. As you can see, using metrics from sklearn, the accuracy score of 0.82 with an AUC of 0.82 in a random forest approach. Again, we'll use an 80-20 test train split and set up the model. Our most important features are destination port, flow duration, and protocol, each of them in the top 3. And as you can see, the results are much better with an accuracy score of 0.99 and an AUC of 0.99. K-fold cross-validation using 10 splits. After running K-fold cross-validation, returned an average of 0.99 across all 10 splits. Let's take a deep learning approach using a convolutional neural network using the Keras and TensorFlow libraries. Our first approach uses the same discretized features from the naive Bayes and decision tree approaches. For this iteration, I went ahead and ran the models ahead of time to speed up the demo. So first we create our variables using an 80-20 test train split. And here we go ahead and define the deep learning function and then instantiate the model. And in here we define the epochs at 80 or essentially 80 iterations of the model. And then as you can see here, through each iteration it tracks the loss in accuracy, and I'll show where those compare to each other at the end. And here the results show a 75% accuracy rating for this model. Then we graph the accuracy over time. And as you can see in the blue line, accuracy increases over time to that 75% accuracy. And then loss decreases over time. The overall loss for this model was 1.24. And our confusion matrix, if you take a look at it, our 75% accuracy, if you add these two numbers up and divide by the total, you get the 75%. There's all 78 variables and takes a multi-classification approach using 3 response variables. Those response variables are benign, file transfer protocol brute force, and secure shell brute force. So those are really the 3 malicious types of traffic we'll look at, and we'll look at this specific CSV file. Just kind of looking across the some of the features here. The deep learning model will look at all of them. You can see them listed here. Initially, when we plot this out, you can see that benign far exceeded brute force and label. So to handle that data, what we had to do is do some data argumentation where we leveled out those labels so there wasn't any bias towards one outcome or another. So again, here we start to create our test train splits. We define our model again here. And this just gives you a model summary. We instantiate our model and begin to fit it. So just like before, we went with 80 iterations, and each iteration tracked loss and accuracy. And you can see here the model fared much better with the 88.5% accuracy score. And the overall loss was 0.388. Now if we plot our accuracy score over time, as you can see here, accuracy did continue to increase but leveled off around the 30th iteration, but remained high throughout the model. And in iterations, around the 25 epic spot declined and then remained level across. And our confusion matrix, because there were 3 different variables here, so you get the output of 3. But if you add all the true positives and divided by the total, you'll get the accuracy score of 0.89.